Morning, and today's topic is just going to be a little bit more on the absolute must-knows of series and Taylor polynomials. So the first thing I'm going to do is show you the document of what you have to know and what you don't have to know, just so you're clear on that. And then the one that I linked for you on your master schedule is the stuff you have to know, and I whited out the whole right-hand column of stuff you don't have to know, because that's where we're going to write. So when you're done, you'll need to submit your notes and the circuit that's attached. The circuit does have a couple things on it that you don't need to know for the AP test. I should have clarified it. It's not that you don't need to know it. It's just that some of this series stuff, due to time constraints, sorry, I'm looking at my banks, got cut off. So I need to share my screen on my iPad with you here, if I can. And then we'll get rolling. So the first thing I want to show you is the stuff that you don't need to know, and the column that also has the stuff that you do need to know. So let's go. Sorry, it takes me a little while to load this stuff. There probably is a better way, but for now, I'm just gonna log on through it. It's early in the morning and I have an AB conference coming up here in a little bit, so I'll try not to go too fast, but because of that, you probably won't have very long notes. They get to do the graph analysis, which you guys have been doing forever, right? And by the way, although there's no, just a second, I think I want the series topics due to COVID. All right, so sorry, I was thinking, but yep, this is exactly what I wanted. So although you guys won't be getting an AB subscore, I'm not 100% sure that doesn't mean you won't have any AB content. That's why I've been on the FRQs. They're very BC heavy, but there's been a sprinkling of the more popular AB topics in there just in case. But here's the document that I wanted to show you before we start. The one that you have has the stuff you don't need to know for the AP exam whited out. So we're going to be focusing primarily on the geometric series. We need to know the sum. We need to recognize them. We need to be able to find that R. We need to be able to manipulate them if necessary to get them in the correct form so that we can find the R. That would be in this form. We need to know our harmonic series that diverges, the sum, as we go from 1 to infinity of 1 over n. We need to know that the harmonic series in the presence of an alternator will converge because the limit as n goes to 1 over infinity of 1 over n equals 0, so the alternating series test makes that one converge. We also need to know our p-series and what makes those converge or diverge. My guess is there'll be some question about find the k so that both of these converge or something. My guess is they'll be tested in kind of one lump sum with some missing, I don't know. I'm guessing. If I'm right, that'd be awesome. We need to know how to verify the alternating series test. We don't need to know, well, we'll talk about what we don't need to know later. We need to know our ratio test, which is good. These are all the ones we were very proficient in, so that's really awesome. And then we need to know how to generate that Taylor polynomial. In particular, we need to know how to get those coefficients. So we'll be talking about that as well. Also, this is still just more of that Taylor polynomial that we need to adjust it when we're moving the center. What we don't need to know is actually most of the stuff we covered. We don't need to know the nth partial sum of the sequence. We don't need to know the nth term test for divergence. That was an easy one. We don't need to be able to run the integral test. We don't need to be able to run either of the comparison tests. We don't need to tell when the series is convergent, whether it's absolutely so or convergently so. If the series converges absolutely, then sometimes regrouping terms, we don't need to know that. We don't need to know how to find the error for the alternating series. And all that you've been taught. I did not teach you Lagrange error. I think I might do that after the AP exam. We'll see, it's not super important, but that whole concept of error is, so we might do that. Sorry, it's kind of dark in here. I'm in my basement, even though I have all the lights on. So that power series and finding the convergence or divergence in the finding the radius of convergence using that ratio test and all that stuff that we did the first unit that you were on distance learning, that's actually not going to be tested. I did put 1 or 2 of those, I didn't, but on the circuit there's 1 or 2 of those. So again, that's the stuff that we need to know on the left. What we don't need to know on the right, what I did on your document, I have to bring it up, I should have had them in as the same one, but I don't. On your document, I think that's this one. If not, I might have to go back in. Yes, perfect. All right, so this is where you're going to take some notes. You'll submit them and your circuit as your homework, and then also if you need help on anything on the circuit, I'll have optional office hours Tuesday night at 6. I'll just have this open if I see someone pop in with a question on the circuit. We'll do those together. So, all right. So first of all, with our geometric series, remember the form that it's in, right? And you need to find the A and the R. Now I know that, let's go over here in the notes, n equals, let's go 0 to infinity of, let's say it was -3 times -2/5 to the n. The absolute value of R is less than 1, so we know it converges. It's in the perfect form to tell to what it converges. So I'm not worried about these. Just be careful with that count, that it's the first one generated when we put that in. So in this case, it's -3, but be careful if that count was, say, at 3, that you put a 3 in there for the first term. What I'm a little bit more concerned about is when either you're given it as the sum of the rules of sequence. So suppose maybe it started, I'm just gonna make a fake one. Maybe it started at -1. And then it went to 2/5. And then it went to -4/25. And then it goes to 8/125 plus, and then the subtraction in there. And then ... To decide on this one, obviously you know your A, because you can see it starting at -1. But remember with this kind, if you're struggling to figure out that R, which on this one actually I made it pretty easy, that you can see it's being multiplied by -2/5, but you can always divide that way to figure out your R, and it'll be calculator active, so just divide, do a math, enter, and get it as a fraction. I doubt you'll have one like that, but just in case. So in this one, my R is a -2/5, and my A is a -1, so the sum of this convergent geometric sequence would be -1 over 1 minus the common ratio. And I guess you could leave that because it's numerically equivalent and we're not going to have multiple choice anymore. But sometimes it's nice to, if you need a number for it, get a number for it. The other thing to watch out for with our geometric series, sorry I took up most of the space here, is when it's not quite in that form and you need to mess around with it. So, and we practiced that quite a bit, so I'm not going to do examples, but just keep in mind that if it maybe looks like, I don't know, 2, and then there's a, let's say a 3 to the n minus 3. Just leave it like that. And then let's say, let's do a 3 minus n. That would be better, sorry. Whoopsie. Dang it, I'm trying to activate my eraser. Sorry about that. All right, so let's do a 3 minus n. This isn't quite in the right form, so make sure that you're okay writing it as 2 times, right? And then I'd have the 3 to the n in the denominator and the 3 to the third in the numerator. And actually, that diverges because, actually, no, it doesn't. I'm good. So I'd have the 3 to the third in the numerator. And I can write that as, if I pull the constant out front, it's actually 2 times 3 to the third. And then it'd be 1 over 3 to the n, right? Which is 1/3 to the n. And then if I had a count, I don't know, going from, let's say, 3 to infinity, make sure when you find that first term, you plug the 3 in. But be able to mess around with it if necessary. We did practice that, so that's all I'll say about that. Our harmonic series, diverges. You don't need to prove why. It's just a known fact that it is the divergent harmonic. Remember, anything of this form, just in case, I doubt you'll have to know it, but is a divergent harmonic due to limit comparison test with the divergent harmonic, but they aren't requiring the comparison test, so my guess is you won't need to know that that's a divergent harmonic. Remember when we put it in the presence of an alternator? This becomes now a convergent series. To what it converges, we don't know. Remember, if you're asked to what it converges, it's geometric because the only other one is telescoping, and that wasn't in the list of needs to know. The P series, sum n equals 1 to infinity, 1 over n to the p. Remember, we converge when p is greater than 1. We diverge when p is less than or equal to 1. Remember that 1 over n to the first is the defense for divergence. So that should help you remember that with the 1 there, we diverge because it becomes the divergent harmonic. A lot of times, you know, they'll throw a little k in there. And it'll say, what value for k does this? And you just have to make sure you set that, if you want it to converge, you set the whole power greater than 1. All right, and we were good at those too, so I'm not too concerned about it. So we've got the alternating series test next. Remember, the alternating series test actually has 2 parts to it. So, and the first part of it was always just obvious to us, so I didn't stress it a whole lot, but it was in your notes, so let's get that down. Remember, if the limit as n approaches infinity of the rule of sequence in the absence of the alternator, if that equals 0, right? So sometimes there'll be absolute value bars around there, but let's do that. If that equals 0, then this would imply that the series converges. And again, this is for alternating series. If we had a viable alternator in our rule of sequence, a -1 to the n, a -1 to the 2n, a negative cosine n pi, that sneaky alternator. But if the limit of the rule of sequence in the absence of the alternator goes to 0, then the alternating series will converge. It means that that alternator is causing in the sum for it to collapse to 0 fast enough to converge. Not the sum to, but for the terms in the series. All right, so the other thing though is you do need to make sure that a sub n plus 1 is less than a sub n. So you do really need to verify basically that they're decreasing in value as you go from one to the next. That's usually pretty obvious, so I doubt you'll have to state that, but maybe I'll find an FRQ and we'll throw it in next week if I can find one where that's necessary. The ratio test, remember what we do with that? That's used for our bigger powers. It's used for when we have factorials, when we have exponentials, when we have factorials combined with exponentials, e to the n, those types of, the higher growing functions, we don't usually use it with the natural log or with linear functions, those types. But for those higher growth functions, faster growing functions, the ratio test says that if we take the limit as n approaches infinity of a sub n plus 1, so we put an n plus 1 in for the n's and divide it by a sub n, and if those have the limit is less than 1, and then we have convergence. Greater than 1 is divergent. equal to 1 was inconclusive. So there's a little reminder on that, and I'll run that test for you in just a little bit with a sample. All right, next up. So for our Taylor polynomial, remember we have some function. We usually called it f of x, but they can call it anything they want. Maybe they'll call it, you know, q of x is some function that's being approximated by a Taylor polynomial of nth degree. So remember, q of x is some function. I don't, you know, who knows? I just, let me go like that. Maybe even like that. And when we take that q of x and we try to fit a Taylor polynomial on it, we need a center. We need a place where we're going to make sure it matches completely. That means they have the same y value on the polynomial as on the function. So if I'm centered, let's say over here at C, it looks like they're using A, but I want to put it in context here. If I did a first degree Taylor polynomial, that would have been Calc 1's linear approximation method, or tangent line approximation. If I did a second degree Taylor polynomial, I'd hit at the center for sure. Maybe I'd, boom. And then if I did, let's say, fourth degree, maybe it'd come in right here, but it hit at that center and then boom. As I up the degree, we tend to wrap the polynomial better. When we don't, that's where we get that, like if it just, if it only converges in a certain radius, that's where we did the power series stuff, but you don't need to know that. So remember what we have there. We get, and this is the thing you need to write out every single time. So we have this function that's being approximated by an nth degree Taylor polynomial for the function. And again, if it was first degree, it'd just be a line. Second degree could be that red parabola. Third, you get how that works, right? We evaluate the function given at the center. My guess is for you guys that's supposed to be a C, by the way. For you guys, my guess is that's probably going to be, oh, dang it, tabular. So you'd I can't activate my eraser, sorry. This right here is supposed to be a C. All right, then we do plus q prime at C, the first derivative, x minus C, again, if it's Maclaurin, C equals 0, over 1 factorial plus the second derivative evaluated at C times x minus 2 over 2 factorial plus dot, 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 the nth derivative at C, x minus 2, sorry, to the nth over n factorial, dot, dot, dot. All right, actually it went dot, dot, dot when I had the nth degree. Now, sometimes they'll give you a polynomial. So watch, maybe your polynomial ended up being q of x equaled 5 minus x plus 3x squared minus 4x cubed. And maybe this was my third degree Taylor polynomial, right, that was used to approximate q of x. Sometimes it'll say what was the third derivative. Be careful that you don't say it's -4. The third derivative at whatever the center was, let's suppose it, well, at 2, right? Why do I have an x minus 2 here? That should be a C. I'm sorry, guys, if I'm messing you up. But the third derivative at the center over 3 factorial is what gave you the -4. So be very careful that you don't think the third derivative was -4. -4 times 3 factorial gave us the third derivative. And in this case, the center would have been 0 because I don't have x minus whatever. So this would have been at 0 and it would have been Maclaurin. All right, so make sure you write that model out. It triggers what you're supposed to do. And that also covers this. So that's really what you need to be very proficient at with your series. However, on the, this is all the stuff you don't need to know. I'm going to go to a blank sheet here if I can. All right, so on your circuit, there's going to be one like this. And again, it's not tested on the AP, but I'm trying not to be exclusive to that. It said to find the interval of convergence for this guy. This is called a power series. The domain It's a function. The domain of it is all values of x that make it converge. All right, so you can see that if I let x be like 10, I'd have 8 to the n over n times 2 to the n. And that 8 to the n is probably powerful enough on top to cause divergence. But if I put a 1 in there, I'd get negative 1 to the n. I'd have an alternating series. And the limit obviously goes to 0 in the absence of the alternator. So a 1 would be in the domain because that would converge when x is 1. So I'm trying to find all values of x. It's going to say find the interval of convergence, the IOC. It's all values of x for which the function will converge. So remember what we do, we run that ratio test. The limit as n approaches infinity of the absolute value. See, it's a good review. I think you're going to have to run the ratio test. So I think it's a good review of that. We go to the n plus 1th term. We divide it by the a sub nth term, but that means multiply by the reciprocal. Good review. And for convergence, we need to have that limit be strictly less than 1, not less than or equal to 1. So then we do a little cleanup. This one didn't have any factorials in it, but remember if there's factorials, like sometimes it might say, you know, x plus 2 factorial. Well, then you have to maybe write it as x plus 2 times x plus 1 times x factorial. Sorry, n. Sometimes you'll have to recurse that, but we did that. So let's go to this guy and clean it up. I'd have 1x minus 2 left on the top. I'd have the n left on the top. I'd have the n plus 1 left on the bottom. The 2 to the n would cancel with this 2 to the n, also leaving a 2 on the bottom. So I'd be taking the limit as n approaches infinity of the absolute value of my reduced ratio, and that, sorry, my eraser for some reason is being, there we go. That has to remain less than 1. So just the details of this. Remember, the n is what's controlling this. X would be a constant in this scenario. X is something going into the function. It's the power series. So all things not involving the count come out front. That would be the absolute value of the x minus 2 and just the 2 on the bottom. Those are not being affected by what I call the count. So this is what I'm left with. I've got n running towards infinity and the ratio of n over n plus 1. Technically, it's infinity over infinity. Technically, it's L'Hopital's with respect to n, but we know it's pretty common knowledge that this has a limit of 1, so you wouldn't need to L'Hopital that silly thing. So I actually have the absolute value of x minus 2 multiplying by 2 on the other side, leaves me with this. Now, this is of the form x minus c less than r. This right here is called the radius of convergence. It means you can stay within 2 units of the center, and my center is 2. So it means it converges within 2 units of 2. So 2 to the right at 4, 2 to the left at 0, I have convergence. But you can just use algebra 1 and say, well, I'm going to squeeze this between 2 and negative 2. But it's nice to understand it in terms of you can stray within 2 units of the center. The center is what's being subtracted from the x, so 0 less than x less than 4. Now, this is where we had to decide whether when we write our interval, whether we at the endpoints diverge or converge. It can be one of each or both. Remember, that requires a test. And we haven't practiced this a whole lot, but we did it. It won't be on the AP test, but what I do is I go put my endpoint of a 0 in here, and I see what happens. I would end up with a negative 2 to the n, so I have an alternator. This is negative 2 to the n, over n times 2 to the n, gone, gone. So in my summation, I would have the alternating convergent harmonic, because it's the divergent harmonic in the presence of an alternator. So with the alternating series test, that will converge at 0. So I know I have a solid dot there, converges exactly at 0. When I put a 4 in, I would have 2 to the n over n 2 to the n, cancel, cancel 1, and I end up with the divergent harmonic, the sum from 1 to infinity of 1 over n. So we converge. So we would have diverge and diverge at 4. Sometimes that'll be written with an inequality. Remember I told you 8, or not, I said maybe when you put in a 10, you can pretty much see it's going to diverge because you're going to have that pull on the top of 8 to the n. You can see that this interval makes sense. And we're done. So this last part was just a good review of running the ratio test. That's why I chose it. And it is one of the ones on your circuit. So your assignment is turn these notes in with the circuit through Google Forms. Hopes all's is wells. And we'll be talking to you guys later. Have a good one.